proportions, we get to look at my friend P hat. I think that should be my new B-boy name. Yeah, what up on P hat? Don't call me that.
I wonder what the other options are.
Yeah, no.
I guess put it
So this is what we're going to do.
But I mean, like,
We're going to be checking conditions again when we go through this. We're actually going to look at M&M proportions and stuff like that as we get through this. We're going to actually get to have some fun and eat candy. And eat candy? Sorry, my nose is full.
you just hear you
Not good. All right, so we want to know how good the statistic p hat is as an estimate of the parameter p, which is a population proportion, right? So we've got a sample proportion and a population proportion. Okay. So if we look at these sampling distributions of Reese's Pieces, which we're not going to bring into the classroom, so that peanut allergy people don't die.
Oh, that's fun.
Yeah? Yeah, we don't want you to.
Crazy.
That was me as a kid too. I grew out of it, so good news is that doesn't. I hate peanut butter. So. I think it's good. Oh. All right. So what do we notice about the shape, center, and spread of each of these things? I know it's really hard to see, but this one is a sample size. So over here on the left-hand side, we have a sample size of 26. So we took 26 Reese's Pieces, and we are looking at the proportion of orange candies, right? So I think they're orange, brown, and yellow, right? So we look at the proportion of orange counties. Why did I say orange counties? Orange candies.
Orange County?
Orange County is a cool place, but that's not what we're talking about. So,
Where is it?
So we got, sorry, a number, we got 400 samples. Sample size was 25, I think. It's really hard to see on the board here. What do we notice? It looks like, well, if we were to compare our centers, our mean is 0.154 for this one. And for this one, our mean is 0.149. Fairly close means, right? Yeah. The one on the right has a larger sample size, but the number of samples is the same. So when we increase the sample size, we wound up with a lower mean, lower standard deviation. But I think the most important thing to recognize is the shape changes a little bit, right? It looks like as we increase the sample size, the shape of the distribution becomes more normal. And that's what we're really trying to get at, right? When you increase the sample size, the shape of the distribution looks more normal. In fact, depending on your sample size, many times you can actually approximate the distribution of p hat using a normal distribution. Check it out. The mean of distribution, so mu sub p hat is equal to p. So we assume that the mean of the sample proportion is equal to the actual proportion, right? The population proportion. Our sample proportion will be an unbiased estimator of our population proportion. So that's why we're allowed to do that. All right, so as our sample size gets larger, our standard deviation should get smaller, right? Our variability should get smaller if p hat is an unbiased estimator of p. Furthermore, there is a very nice formula right there. P hat, count of successes in your sample, divided by your size of your sample. That's how you're going to get your sample proportion. Whew.
Fun.
Yeah, we learned that the mean and standard deviation of a binomial random variable x
No.
are those things, right? It turns out that we have a similar thing. It's essentially a proof of why we can estimate, and we can say that mu sub p hat, right, the mean of our population proportion, is equal to our actual population proportion. Sorry, or the mean of our sample proportion, sorry, is equal to the mean of our population proportion. And then, really, you're going to use this tons and tons and tons. And you will indeed use these two together tons and tons and tons.
Like a lot of times.
A lot of times.
Many times.
For the rest of the semester. It's going to come up in every single chapter, every time, as we do inference, as we do all different forms of inference. These formulas will be what we'll use to, a lot of times, to perform normal probability calculations for population proportion based on some sort of sample proportion. All right. So it's kind of an interesting little derivation, but not necessary that you know how to do the derivation. And here's the actual breakdown of your formulas for a sample proportion. Honestly, I say that those are really important. Well, almost the most important thing on here is this right here. You are going to use that a ton. So you're going to be asked a problem, and you are going to have to make some sort of a statement about it. Oftentimes, you'll want to use some sort of normal distribution, right, in order to calculate a probability, a proportion, something like that. Before you can do so with some sort of sample proportion, you have to check that the sample size times what you would estimate the actual population is greater than or equal to 10. Which is fairly simple, right? This is usually going to be a fairly large number, n times p. And you need to check that n times 1 minus p is greater than or equal to 10. You must check both. If you do not check both, then you lose points. So this is actually something that an AP grader will look for, that if you're going to perform some sort of calculation using a normal distribution for a sample proportion, you have to check those two conditions, or else you lose a point. You'll lose something. You'll go from an E to a B on whatever that problem is. These guys are cool. Look at them. Yeah. I wish I was a cool cartoon person.
You sure they were cool?
I don't know. Maybe not this guy right here.
That's pretty good.
I mean, if I had to wear a mullet and have a vest
I
on,
don't know, they look like they
I
go
guess
for
that's what I would go for.
Criticize you for no reason.
Really? The guy with the mullet and the vest?
Yes.
I'd like to see him try.
Honestly.
Go find something.
Don't
Okay.
find something.
Okay.
Always you. Every time.
So here's a picture of it.
I know I was like the most.
No.
No.
I really not sure what we're talking about over here. So this is everybody, I guess. This is a weird picture. But anyways, this is what it looks like when you approximate it to a normal approximation. Your mean is going to be your actual population proportion, and then your standard deviation is going to be represented by that quantity right there, the square root of t times 1 minus p over n.
It's like, whoa.
Hey! I knew we could do it. 7.2 is done. So we'll go over some examples from 7.2 tomorrow. And we're right back on track.